You're now hiring. Here you go.
All right, so questions on the homework?
Yeah. Definitely.
I left my book at home.
You can borrow mine.
I'm good.
So, if you take a look at what's going on here. So we did this one.
Yep.
And I went under, which I
Okay, so
remember.
we got that point load. Yep.
So that's just the first one.
Yep.
And then the second one should have been normal, but like my bend curve just kept getting bigger. It wouldn't go back down. So I don't know what's going on anymore.
You call it R1, right?
Yeah.
And
So R1's 6,000.
6,000. What's the magnitude of this?
16. 16,000.
16,000. Okay. And then this is 10 foot.
Yep.
Is this 4 foot or 6 foot?
That's 6 foot.
And this ends up being 6, and that's 10.
Yeah, it's 16 foot total.
Did you say R1 is what?
R1 is 6,000.
Is
R2
R1
is
6,000 though?
I have it reversed.
Which reaction is
Look,
point load?
I haven't even got the grades back on this, so I probably just did this one completely wrong from the other assignment. So that's going to lead me to go wrong anyway. You know what I mean? So,
Yeah, I think, yeah.
so that's how it's set up. I don't know what R1 is apparently. So there's the first problem. So fuck.
So, do we have any forces in the X direction?
Tested on
No.
this stuff.
Okay.
Ugh, terrible.
The book you can't.
What are forces in the Y direction?
At 16,000
Okay.
and R1 and R2. Okay.
Okay. So R1 and R2 have to equal 16,000, right?
Yep.
So do you want to look about R1 or do you want to look about R2?
Let's start at R1.
Okay.
So I put R1 equals 16,000 times 10.
Okay, so if you want to look about R1 though, how far away is your point load?
Okay.
6 feet.
6 feet.
6 feet, right?
So I just did it backwards then.
Yep. So if we're looking at the moment about R1, right, we've got 16,000 pounds trying to rotate clockwise. And it's at a distance of 6 feet.
So when you check your notes from before, like I remember solving for the moments way in the beginning, and you look at the notes, so it'd be like, okay, R1 equals 16,000 times the rest of the length, and then plus R12 times 16, and then you take those two values and divide it by the 6. I don't know.
Say it again.
Never mind, man. I'm just gonna burn my notes. It's easier.
You have to remember though, if you're looking about this point, what's causing rotation? Is R1 causing rotation?
No.
Why not?
It's going through that point.
It's going right through that point.
I'm saying those,
Right?
when you put R1 equals, you figure it all out and it gives you R2.
Correct.
And then you minus that off the total and that'll give you R1.
That is correct.
Yeah. So that's what I was saying. If you do R1 equals 16,000
We're not doing
times
R1
the-
equals though.
Okay.
We're looking at the moment about R1. Right?
Okay. I'm trying to follow you. I got
What's
like,
the difference between the two?
I don't know.
Between what two?
You're saying between R1 equals and the moment about R1 equals.
Well, you have to use this to determine R1, right? If you do a moment about R1. Because R1 travels through this point, so you're not going to solve for it. If you want to solve for R1 first, you'd have to take your moments about R2.
Okay.
Does that make sense?
It's getting hard to distinguish between all these different phases that we went through, from what we started working on into the next part, and then shear, and then to the bending. Like when I go to solve these, I don't even know what equations I'm doing or where I start and what I cut out.
But are you starting with equilibrium? Or are you just trying to jump to solving your problem?
Well, I was just using what I already did that right here in the last assignment, which apparently is not right.
Okay.
So,
Well, I think that you just have them mixed up.
yeah, that's probably gonna change a lot of things.
So if you're taking your moment about R1 and you have clockwise rotation, 16,000 pounds times 6 feet, what else is interacting on? R2.
At negative
Okay? And how far away is R2?
16.
16 feet away. And remember that in order for this beam to stay in place, this has to equal 0, right? If this doesn't equal 0, it's going to spin off. So I don't know if that's where you're having confusion with it. This isn't being set up to say that we're solving for R1.
That's probably why.
We're solving about the point where R1 is located. Okay? You're solving for R2. Just like if you were to say the moment about R2, what would that equal?
16,000 times 10. Negative R1.
So I was just looking at it wrong and doing it
Careful.
backwards.
Or R1 times.
If we're looking at R2, how is this trying to rotate? Is it trying to grab and rotate this way?
Negative.
Or is it's going counterclockwise, right?
Negative.
Okay? So you have to remember that if you're taking a moment about a point, it's going to give you the other reaction is what's going to kick out. Okay? And then you solve for that one by going back to your f sub y calculation.
Okay, so if we take, so that one should have been a lot easier. I'm sure my calculations will work out now.
Sorry. But we should also be looking at these, right? I mean, we've also worked enough of these problems. I certainly can't come up with magnitudes looking at these things. But if we look at the location of this load, which reaction needs greater capacity?
R1.
Why does R1 need greater capacity?
Because it's closer.
It's closer to the point load, right? So it's going to pick up more of that load. Okay? Now, the analysis that we're doing is very straightforward, right? We're looking at one section. And so in the real world, there's a couple different ways that we could deal with this. What this could mean is we need a bigger footing there, right? If we need greater capacity. What it could also mean is maybe we're just looking at a portion of a larger beam. Maybe we're looking at an entire bridge deck. And once you start doing the analysis, maybe everything is the same, okay? And we're going to be able to build everything to the same size. We also may find in our analysis that we have all different types of values. And for ease of constructability, we may just build to the largest point. Okay? So that's how this is actually taken into account in the real world. But it's not just, this isn't just for pure academic purposes that I want to have you guys writing on a bunch of sheets of paper. So
cool, that was assignment before, so if we do this assignment and do the bending thing for it,
yep.
mine turns out now that if you just swap them around, but I was doing, unless somebody else needs to see this one on the bending scale, it was supposed to be the easy one, but I was doing the next B.
Well, so do you want to look at the bending
And
on
we
this?
can, yeah, we can check it out if you want.
Okay.
That way I make sure that.
So draw your shear first, right? So what does your shear look like?
So it goes up 10,000 right away.
Yep.
Goes over 6. and drop 16,000 to that -6, and then finish it there.
right?
Yep.
Okay? So all our point loads, if we're only dealing with point loads, this is how your shear graphs should always look, right? Just nice blocks. What do our uniformly distributed shear diagrams look like? That's when we have triangles, right? Okay? Okay, so where is your maximum shear occurring?
6 feet.
Okay? Or I'm sorry, it's not your maximum. Where does V equal 0?
6 feet.
At 6 feet, right? That's where we're crossing. And where does our V max occur?
6 feet. Or no,
One.
10 or 1.
All right.
At
Mark
reaction
that.
1, right?
Or it wouldn't be 1 foot. It'd be, yeah, reaction 1. Yeah.
Yep. Okay.
Yeah, see, I didn't even have that for answers. I didn't even know the answer.
Okay, so where is your maximum bending going to occur?
6 feet.
At 6 feet, right?
Because that where it's got the biggest change,
It's the lowest.
or where your biggest load is.
Where we reach 0, the definition of that point is where our maximum bending will occur. Okay? So for your bending,
So I did.
what does it look like when x equals 0? And remember, the bending, just like shear, we're just moving left to right.
It's at the line.
We're right at the line, right? And we're looking to the left of it, so nothing's trying to cause rotation. So it's 0. Okay?
Is it good to always start out at 0?
I would. Yeah. I mean,
It was always going to be 0 though. It's
By-
bending.
if we have a simply supported beam, yep, where our supports are at the beam termination, your bending moment will always be 0, right? Because if you're working left to right, you don't have anything to the right of the beam to cause rotation, right? And we can't cause rotation if we're pushing through that line of action. Okay? So, simply supported beam, when we're doing analysis at the supports, your bending moment will always be 0. Okay? What about at x equals 1? Keep in mind we're moving left to right.
1 times 10,000.
10,000 pounds times 1 foot, right? Clockwise or counterclockwise?
Clockwise.
Clockwise. Okay. What about when we get to 6 feet? What's happening?
16,000.
60,000.
Careful.
10,000 times 6.
10,000 times 6? Yep.
Hey, 60,000.
Right? Okay. Do we have to take the 16,000 into account?
No,
Okay.
I said 60. Let's do what?
Still got
Banging
lost.
on the door.
So it'll be 60,000 pound feet now. Okay.
Yep. Okay, what happens when we get to x equals 7? Okay, so now we're a foot away.
So you do 7 times 10,000 minus 16 times 1.
Right?
Well, it would be plus or negative then.
Oh, yes, sorry, thank you. Yep, because this is providing counterclockwise rotation, right? So that becomes up 54,000. Okay, so starting to drop off, which is what we want to see, right? Okay. Then let's jump out to, we can just look at 12 feet. That'll give us enough points.
Well, in the homework you said 3 would be good if we got the max.
Yeah, absolutely. I just
So
want to make sure that we're understanding
Yeah.
conceptually what's going on.
on looking at your shear, and when it's something pretty simple like that, which I'm not sure is on a lot of them,
Yep,
you know where your max is just by looking at it.
correct.
So you can start there, pop to the left and pop to the right, and as long as you got something that, okay, it's gonna terminate on the ends,
Yep,
that's good.
yep.
Okay.
Yeah, if this is what you have for your beam, this is what our shear diagram is going to look, right?
Yeah,
Now, if we move this over 3 feet, what are we going to do?
Just move your vertical line.
We're just going to move
Yeah.
this 3 feet, right?
yeah,
Okay? And if instead of having a point load, if we have a uniformly distributed load, and that's all, what's it going to do?
so that was my next question. The shear diagram will just be if it's uniformly distributed, like 750 pound, it'll go up and then slope all the way down to the
Yep.
bottom.
Yep. Got it. And then how do you determine your max shear there?
Where it crosses.
Just where it's crossing zero.
Yeah,
Yep.
I just have so if it's, let's finish this, because that's the one I got a question on also.
Got it.
Depending on where you put your-
So we're what, 6 feet away there?
I did 3, 6, and 10. I was like,
You just drop off.
So 120 minus 96, so 24,000.
I wish I had the answer to this back, because now I don't know if like I'm gonna be
You
starting.
did fine. Who cares?
Oh yeah, I was wrong on the first one. So am I gonna be wrong on all my problems? Probably.
Okay.
On your dude system.
Yeah, if I can get graded on consistency, if I'm consistently wrong,
Consistently wrong, that's good.
you know, 'cause my R1s and R2s are backwards.
Well, yeah, if all we're doing is flipping up our R1s and R2s,
I know, but
that's
now,
not the end of
you
the
know what I'm
world.
saying, A through F is on what we've done before, and I don't know if I'm wrong on every single one.
Well, if you're just doing them backwards, all you're doing is you're just taking a truss or a beam, and instead of doing that analysis, you've been doing this analysis.
You're looking at it from the other side.
Well, I get what I'm doing,
Yeah.
but they're not all that simple, so, yeah, okay.
Yeah. Okay. So, does this make sense? And yes, I agree, Rush, that I'm not expecting you to calculate it
Yeah.
at
No, yeah, I
6
get it.
points, at 8 points, at 10 points on a beam that has 1 point load. Okay? I would say check 1 point on this side, check 1 point on that side from a homework standpoint, and I'd be fine with that.
Okay.
Where you have to be a little more cautious is if you start looking at 2 uniformly distributed loads and a point load, making sure that we're checking in what's going on at the termination of those points, okay? So, do you wanna look at a uniformly distributed load?
Yeah, so we got one that's just 14 feet long, and it's 750 pounds a foot.
Okay,
That's the only thing on it, and I was building my bending diagram, and the thing just kept getting bigger, like it didn't start going back down. I know. Not sure why.
your bending diagram didn't start going down? Okay.
Yeah.
Yep,
That's not a bending diagram.
okay, so,
No,
what did you say it was 750?
Yeah, 750.
Okay,
So,
so what forces do you have in the X direction?
50, oh, none.
We don't have any, right? Okay, so we're good there. What forces do we have in the Y direction?
700, or R1, R2, and then
50 times 14.
4, yeah, hold on. 10,500. Or that.
Okay. So R1 plus R2 have to equal 10,500,
Yeah.
okay? So which point would you like to look at for the moment?
R1.
Okay, so the moment about R1. Do we have to take R1 into account?
No.
Okay? What about our uniformly distributed load?
Yes,
And what is it doing?
pushing down.
And how do we resolve it? What do we do with uniformly distributed
Cut
loads?
it in half,
Cut it in half.
7 feet.
So it's gonna be 7 feet away, right? Okay? What about R2?
That times 14.
Yep.
Ooh, I can tell I got this wrong.
In what direction is it operating? Is it trying to rotate this way, or is it trying to rotate this way?
Negative.
It's a negative value, right? Okay? So, R2 has to equal 10,500, so that's 73,500.
Oh, no.
Right? Did I figure that right?
Yeah,
I don't even know how you.
so 5250.
Oh, okay.
Okay?
So R1 would be positive though,
Yeah, it's going up.
and R2 would be in the negative.
No, or one.
They should both be positive, right?
Yeah, because they want to resist the.
Because we have a uniformly distributed load. In this particular case, aren't we saying the same thing as if we put a point load?
So does your shear diagram not go down at an angle?
Shear diagram will, yes.
Okay,
Our shear diagram
so
will.
the shear diagram's gonna end at negative 5250.
Correct.
Correct.
Okay, that's,
Yep. And
that's what we did
remember
great on
that
school.
depending on if you're looking at it left to right or right to left, the magnitude of our shear diagram is just based on how we start our analysis, right? If I start at reaction 1, I'm going to have 5250 positive over here and negative 5250 over here. But what happens if I start from R2? I'm going to have a positive 5250 over here. I'm going to have a negative 5250 over here, okay? Does our beam care if it's being acted in this direction or it's being acted in this direction, okay? That's just what we're using to figure out what's going on, okay? All the beam cares about is the magnitude, okay? So your shear diagram, you'll start out here, 5250. Like we said, we already know that we're going to be 5250 over here. How are we joining them?
Straight line.
The straight line, right? Constant slope of 750 pounds per foot.
That's right.
Okay, and that should occur at 7 feet. So what do you know about the angle, or I'm sorry, the area of both these triangles? They
They're,
have to be the same, right? Okay? So if you look at the bending, and so Rush, if I'm understanding your comment right, your bending is going like this,
yeah,
okay?
it's awesome.
So let's look at m of x equals 1. Okay, so we're 1 foot away from R1.
So it'd be
Yes, that
was it.
750
What's happening?
times.
So it's 750 times 1.
Is there anything else we need there? All you're giving me is a force.
And then a half foot.
Okay? What type of rotation is this trying to make? Is it trying to make clockwise rotation, or is it trying to make counterclockwise rotation?
Clockwise? Counterclockwise?
Why do you think it's trying to make clockwise rotation?
Are we going from R1 or one?
We're going from, no, we're right here.
Oh, it's going down.
And so we're resolving our force here, okay? And you're going to grab on to your beam 1 foot away from the, 1 foot away from the reaction. This force that's half a foot away, operating, it's going to be negative, right? It's going to be operating counterclockwise. Okay? What about R1?
What about R1?
Positive.
Do we have to take it into account? Is it going to be trying to rotate 1 foot away?
So it's 5250 times 1.
It's going to be 5250 pounds times 1 foot, right? Does everyone agree? Mm-hmm. Okay.
4875 is the answer.
So yeah, 375. Yep. Okay. How about x equal 4? We just need to plug and chug, right?
Negative 750 times 4 times 2.
Right?
Yeah. And then times or plus 5250 times 4.
Okay. Minus 6,000. Plus 11,000. Okay. So, what about x equals 7?
That's 5250 times 4. No, it'd be
It'd be 21.
Oh, sorry.
I
Yep.
was just like, what? 21.
Yep.
So it'd be 15.
Better? Thank you.
Yeah,
Yes, I imagine that does make more sense.
it does now.
Okay, so what's going on at mx equals 7?
750 times 7 times 3.5.
Right? So that becomes,
So 18,375.
and that's 35,000 and 1,400. So it's 36,400.
It becomes
Your
18,375.
answer is 18.
Oh, that's everything.
No, that's,
Got it.
well, no, that's the first part and the answer. That's 750 times 7 divided by 2. And it's also the answer.
36,750
It's double that. So it just happens to be the answer also.
R1 times 7 feet. 5,250 times 7 is 36,750.
Gotcha.
So you
So
have
it's
negative
eight-
18.
It's 18,375 twice.
I gotcha.
All right.
Plus 36.
Got it.
7.
Okay, so then let's see what's happening at,
So, this is where.
okay, x equal 9.
9.
Let's do x equal 10, sorry, because it's going to be easier to do the math up here. Right? Okay.
Ends up being 15,000 again.
Okay, and we're
How, wait,
3 feet away, right? From our maximum on both these sides. And we're getting equal magnitude. What does that mean our curve is going to look like?
Symmetrical.
It's going to be symmetrical, right? Our maximum in the middle, and it's going to be parabolic in shape. Okay?
how's that?
You have 7,500 times 5,
10
So
times
it's-
5.
3750, right? Or 37,500 plus 52,500.
God bless you. Thank you.
I know what happened.
Okay?
So I was
So
putting in my
15,000
calculator wrong, because I was like, okay, it's 750 times 15. So the 10 times 5,
So
You come out with-
50 times. Okay.
comes out with a completely different answer.
Yep, and that's why I guess, from my perspective, I would recommend that you guys always write this out. I know that when we look at something that's 1 foot away, and you'll just say, oh, it's 6,000, write everything out, right? And then it's easy to reduce
Well, I
it.
had it wrote out, but like
Got it.
still plugging it
Just
in there.
plugging it in.
I skipped
Got
that
it.
step.
Got it.
Like, I gotta tell you, man, if we move on to like another lecture and I'm still back down here, I'm gonna feel completely drowned. I feel like we're 2 weeks ahead of talking about, and then going back to the homework is just crazy, man.
Have you posted the answers for the,
I have not.
can you do that so we could
Yeah.
at least make sure we're using the right
Yep.
reactions?
Yep,
Yeah, so that we don't have to redo it twice.
sure, sure.
So that makes a lot more sense on that one, because I knew 7 feet had to be the max.
Mhm.
You know what I mean? And then I did 10 feet and it went to 41,000 because I messed up the,
So did you check it at another point?
it kept going up. I kept doing the same thing.
Okay.
You know what I mean?
Doing
That's,
the
that's
same
where I
thing.
stopped, and that's when I emailed you. I was like,
Gotcha.
this does not look like anything in my notes. 'Cause
Gotcha.
the first one, you remember, I went below the line.
Mhm.
And then this one just kept climbing. I was like, okay, I'm recording. So,
Yep. Do you also want to look at a combination?
Yeah.
Yep.
is that like the third one?
Yeah, D, no, fourth, big D.
I don't even know if I did that right.
Okay, grab your book.
Yeah.
Grr.
D.
Where's your oldest one? Did yours look like that?
Which one is that, number 4?
D. Yeah.
Sure did.
Yeah. I think we did that one class actually, but whatever.
I'm pretty sure we did.
All right.
Pretty sure we did D and E in class.
Why didn't we check C then? Let me see C.
Because C's easy.
I mean, I
It's all pointless, you just step down.
Yeah, draw the damn bubble for it.
Oh, that's not what I'm doing right now.
Yeah, exactly. Don't call anything. Nothing's easy. Alright. B. Steve, you said the next part is we're solving for everything then?
We
Yeah, but I don't know how to do numbers yet. I don't know how to take into account the order.
I had number 1 wrong, so,
You did?
yeah, I can't wait.
Walk me through it.
Yeah, it's gonna be fantastic.
Okay. So, we don't have our
What is the
reactions.
Distance.
18.
18 feet, 10
Well,
on the left
10.
side, 8 on the right side.
Yeah.
God damn, I had it all.
What?
10 on the left,
More?
then 8
Oh.
on the right.
Alright, I'll figure it out.
It's how much?
I don't know, it's just the distance
Are they doing it here?
Oh,
from reaction 1 to.
gotcha, yeah,
12,000.
yeah.
Yeah, that's where you need to be.
He's doing it here?
Okay, I'll be up in a minute.
Because I'm like right next to you.
Yeah, right.
Bro.
Okay,
You
so
getting glass put in there?
Yeah,
Do you need to move my truck?
I'm just doing my truck.
0 forces in the X direction, right? What about in the Y direction?
12,000.
Okay?
Plus 200 times 18.
Well, we want to minus that, right?
What's that?
You're not gonna.
He's got to inspect because it's.
Minusing a bolt?
leaking.
Yeah, oh, yeah, right.
Right?
Replacement.
I mean, we don't have to.
Right, I'm just accumulating them.
Yep, yep.
I thought it was
I don't know
nice.
what's.
Okay, so R1 plus R2
What am I doing?
is going to equal 15,600. Okay? Now, do you want to look about R1 or would you like to look about R2?
R1 plus R2 equals. Okay. R1.
Okay? So what do we have?
So we have 12,000 times 10.
Okay? What about our uniformly distributed load?
3,600 times
3,600 pounds times 9 feet. Right? So Jay resolved the force into a point load. It's occurring at the midpoint. Okay? I'm sorry. Is this 8 feet?
It'd be 10 feet.
It's 10 feet, right?
Alright, I was about to lose my shit. I was like, wait a minute.
Now what about R2?
R2 times 18. What was that middle one? 36.
Our 3,600
Okay,
pounds times
yeah.
9 feet. Okay? So is our sense correct on all of these? Are they all causing clockwise rotation? About R1?
Not R2.
No,
Not R2. Okay? That's our negative, right? When we're grabbing on here, our 12,000 pound is trying to turn this way, right?
Yeah.
Our uniformly distributed load is trying to turn this way, but R2, our reaction here, is trying to push everything that way. Okay? So R2 equals 120,000 plus,
So I got 152,400, but
152,400.
let me check 3,600.
No, I got 152,400.
Oh,
Yeah.
for this
The
sum.
total, yeah, the
But then you
total.
divide by 18.
Then divided by 18. Oh yeah, sorry.
Yep.
Was the 8,467. To make it simple.
8,000.
84.67 is what I got. So what do you think?
Okay.
Well, I got .666.
Well, yeah.
Same thing.
And then you just take that off of the.
Do we subtract that from our
Yeah.
15,600, right?
Email.
Stupid colleges, I keep trying to.
Does that make sense when we look at our beam?
Yeah.
Yeah.
That we have more capacity needed over here at R2? It does, right? Because our point load is closer to this reaction. Now, it's not that much closer, right? It's
not
only
that much
1 foot off
different.
the center, so they're a little bit closer than some of the other problems.
Yeah.
Okay?
Okay.
So what does our shear look like?
So R1 would go right up to 7133.
Mhm.
And then for 10 feet, you angle down to 5,133.
Okay?
So it'd be
Because you're
2,000.
you're losing 200 pounds per feet
Yeah,
over 10 feet.
so 2,000 pounds less over 10 feet. And then you. Then you drop straight down 12,000 to 68, 67.
And that should be a good indicator to us, right? We know that we're changing 200 pounds per feet, and we drop down, and we're at 67 feet in our tens and ones places. So we know that we aren't changing our tens and ones places when we're using our uniformly distributed load.
Definitely.
So we should be able to get at least in the ballpark, right? Okay. So now what are you going to do?
So it continues on that slope to the negative.
846.
Yeah,
8467.
Yeah.
Okay. Yep. So 200 pounds per foot over 8 feet. So 1,600 more pounds, right? So it's going to drop us down to 8467. So where is our maximum shear occurring? R2. At R2. Where does our shear equal 0?
At 10 feet.
When x equals 10 feet, right? When we're moving left to right. Okay, so now we're ready to draw the bending diagram.
Hey, on that last one, when we did it was just straight 750 pounds across. So you had 5,200 for R1,
Yep.
and on the 5,200.
Negative 5,250.
So the max shear is it just equal all the way?
It's going to be 5,250 at both points.
Okay.
When the reactions are equal, your maximum shear will occur
Okay.
at those points. And the only time that's going to occur when either all your load is in a point load at the center of the beam,
Center.
or you have a constant uniformly distributed load over the entire beam, right? So we see that all the time in the real world, don't we? That's what happens with all our materials, right?
Okay, that makes sense.
It works out really great in a classroom setting, but it's very rare that that's what actually goes on in the real world, okay? But it's something to be aware of. Okay, so what happens at x equals 0?
0.
We're equaling 0 again still, right? Okay, because we're simply supported. Okay? Let's go to x equals, let's just start at 4. What do we have to take into account?
So it'd be 4 times 200, then times.
800.
Okay,
But you gotta divide.
so our 200 pounds per feet times 4 feet,
And times 2 feet.
and it's located 2 feet away, right? Okay, how is that acting? Let's see, that's 10 feet.
Negative.
It's causing negative rotation, right?
Yeah.
Anything else?
And then the 71.
Our reaction,
Yeah.
yep,
The,
How far away is that?
18 feet.
4 feet.
Careful.
Oh, I thought you said R2. Oh, I thought you were talking about R2.
Nope, we're looking at, remember when we're doing bending moments, we're either moving left to right the entire time or we're moving right to left the entire time. Okay? So we're 4 feet away. Okay, so that's minus 1,600 pound-feet plus 2,800, 3,100 plus 32, 33. Is that correct? 1633?
70. Hold on. 71.
Oh, sorry, no, that's 7,000. Ugh,
So 28, 532.
off the order of magnitude. So 28,000.
28,532.
That'll look a little bit better, right? Okay.
26,932.
Okay. Now, what happens to us when we get 10 feet away?
So 200 times 10 times 5. Or, well, that'd be negative.
And that'd still be negative, right? Yep, because we're traveling in the same direction, so our loads are still going to have the same effect. Okay? What about our 12,000 pound load? Is that having an effect?
Not,
It's passing through that line of action, right? So it's not causing any rotation. So that becomes negative 2,000, negative 10,000 pound-feet. Okay, so 61,330 pound-feet.
yep.
Okay, how about x equals 14?
So it'd be the 4.
Negative 200 times 14 times 7 plus 7133 times 14.
26,932 pounds.
Okay.
But wouldn't you?
Do we have to take anything else into
Yeah,
account?
the 12,000.
We need to have our 12,000
That
pound
came
at
at
this
10
point, right?
feet.
Because now we're over here. Okay?
Where were we at? 14. So 12,000 times 4.
Yep. Now this distance is
Negative.
4 feet, right?
Yeah. So negative 12,000 times
Yep.
4.
Okay? Everybody see that?
Yeah.
Okay. So now you can sum everything up. $90, $98, $92.
62?
I got 75, 460. What'd you get?
99, 862.
862?
What the fuck?
Okay. So now we're at 51,862, 31,862,
What's the negative?
32,262.
Where'd you get 48,000?
Where'd you get 48,000? That's only 12.
12,000 times
Isn't this 12,000 pounds times 4 foot?
Okay, that's right.
Right? Then I just switched
Yeah.
the terms.
I got you.
This is a lot easier for me to do that in my head than do that in my head. I gotta think a little harder on that one. But then, is this right?
Yeah, that's right.
Okay. So are we happy? Where's our maximum occurring?
At the 10.
At 10 feet, right? It's our maximum value that we see here. That's what we said based on our shear diagram. Okay? So now we can plot some points. We'll go ahead and assume that because we looked at here, we know what's going to come when we look here, right? We look all the way. So 26,932.
So the max would.
Go ahead, Rush. Sorry.
Oh, I got it.
Do you have to do the 18? I mean, if you do the 18 feet, should it equal 0?
Yeah.
And if you, let's say like you're close to it, is it fine, depending on how you round, I guess? Like, let's say it's like 10 or -5 or -6 or something.
Oh, if you calculate it out and you get -5 pounds or 10 pounds or something, yeah, you probably have some sort of rounding.
I mean, like, are you
Something
gonna
is-
just down, are we good to go, or are you gonna?
Yeah, I mean, if you turned in homework and you had m of x equals 0 and m of x equal 18 on here, and you have a non-zero number, I'll be honest, I'm not looking at that.
Okay.
I mean, well, I guess if you draw this and show me this, and then you turn this in and you say that you have 10,000 pound-feet, I might take some points off for that. But if you say that it's 10 pounds per foot, I'm not gonna, yeah. That's fairly inconsequential. But we should understand at this point that if we have a simply supported beam, okay, where our reactions are at the termination of that beam, your moments at your bending moment at that point is gonna equal 0, okay? If it doesn't equal 0, we no longer have static equilibrium and our beam is rotating, okay? So we're not gonna have a happy owner, even at 5 pounds per foot. Okay? These make sense? Ish? Do we need to look at a beam where we are not simply supported?
Yes.
Okay.
What does that mean?
Where you have that overhang.
Oh,
Where you have a portion that's,
yeah.
another way to look at it would be if we were talking about a cantilevered portion.
Okay.
So, simply supported beam just means we have one span, reactions are at the points of termination.
Okay.
So. So, what would you like to look at?
Is there one?
I'm up for it. I don't have my book with me, sorry.
Oh,
So I can't generate something for you.
Steve, you got,
Any one of them.
well, pick one.
Hey, let's do the first one.
Okay, so what do I need to know about it?
I don't even know what page you're on, bro. 102? Is that where you're at?
Yeah.
So it's,
4, 7, 4,
R1 is
19.
4 feet in.
Okay, what's the total length that I got, 19 feet?
19.
Okay. Okay,
R2's at the end.
R2's at the end.
We have a 500-pound point load, 4 feet to the left, R1.
500 pound?
Yes,
Okay.
you got a 1,200 pound, 3 feet to the right of R1.
£1,200 pounds? Okay.
5 feet from R2, come back 5 feet, you got 800 pound load. You got 7 feet in between the two.
Okay. 7 and 5 12s, yep. So 7 feet in between. Okay, so.
Holy crap.
Right, so it's determine equilibrium. Do I have anything in the X direction? Nothing's acting in the X direction, right? So we're good. What about the Y direction?
500, 1200, 800, R1 and R2.
So R1 and R2 got equal 2,500.
Yep. Everyone agree? Yep. Do we want to look about R1 or R2?
I have no idea where to start on these things, so
R2.
R2.
Okay. So 500 pound force.
So, what's the total length on this thing again?
19 foot.
So would it be 500 times 19?
Maybe negative 5.
Yeah, wouldn't it be negative?
Would be negative, right? Because remember that we're going to grab on here. And that's going to try and, these guys on top are going to try and rotate this way.
Okay.
Okay? Our reaction at one's
R2 is no, all on the same direction.
going to try and rotate that way.
You have the other one and then that one. Okay.
That's why I said right.
Sure.
Okay, that makes sense. What are you doing with both? No,
We can, let's plug through R2 and then we can look at R1 and see what happens. Okay? What about R1?
R1 times 12,
Plus
15.
R1 times 15. There you go. Okay, our 1,200 pound?
Negative.
negative 12,
Oh,
or negative 1200 times 12.
Yep.
Wait, what was 15?
R1 is 15 feet away. So we have 7
Oh,
feet in
because you
here.
gotta take it in, okay.
Yep.
Alright, so,
And then 800 pounds?
At negative 800
How far away is it?
pounds.
5 foot. Okay. Everyone in agreement? Okay, so R1 is going to equal all this mess, 9,000, no, 9,500. Plus 14,400. Plus 4,000. All divided by 15, right? Everyone in agreement?
Shouldn't you have some negatives in there?
well, no, because you're.
I moved them over.
Uh,
I moved R1 to the opposite side and then divided by -1. Or moved it